then what I can do is I can take an analytical approach and go ahead and solve. So the information that we have from the two of the constraint is that H is equal to capital H and multiplication of L, W and H is equal to capital V. I can take that, and from there I can take this L equation. I can write that L is equal to capital V, right, divided by W H, right? That is what is the L is going to be there. So I can take this from this equation and I can write that L is equal to capital V divided by WH, and I can substitute that in my objective function. So now let's take what is our objective. Our objective was to minimize the material, the volume, which was given by this equation. What I will do, I have done this substitution. From here I have written this. In fact, I can go back and I can write this one too, capital V divided by W times capital H, because this H is equal to capital H, and that also is given here. So I can write this equation, right? So now I will take this one, and wherever I have L in this overall objective function, I will substitute this, and that will give me and eliminate the variable L in this overall equation. Okay, so let's do that. Let's take this and substitute this at different locations in the objective function where this L is and see what happens. Okay, so now I can take this equation, I can substitute this, and I can write this overall equation as this, right? 2W instead of small h, since small h is equal to capital H, we have written that, and then we have 2L times H, which is V by WH times H is equal to capital H. From here, that's what we brought in here, and similarly W times L, we have substituted this small l by capital V divided by WH, and that's what we have written here. So this becomes my next function, and what you have done here, we have essentially eliminated the L from this function by using the information that was there in the equality constraints that we have. Now, what I can do is I can simplify this equation, I can cancel out. So for example, you can see that H here and H in the denominator will cancel out. Similarly, the W here, and this here will cancel out. So you can cancel out term and simplify this, and from there you will get this simplified equation. Okay, so if you look into this equation, one of the things that you should see that this equation is only function of W. W is the only variable that is there. All the other things like capital H or capital V, those are constant. So by substitution, we eliminated L and we came up with a function which was purely a function of W. So what we have done, we have recasted our problem, optimization problem, or the goal or objective function, and by substitution, we have arrived at an equation which is only function of a given single variable. Now, what is our objective? Our objective is to minimize this material, and we know from calculus that if we are interested in finding the minima or maxima of a given function, then I can take the derivative of that function, okay, and set that equal to 0, and that will help me in solving the problem, right? So if I take this, fw, and if I take the derivative of that fw and set that equal to 0, then from my calculus, basic calculus concept, I will be able to solve and find the minimum of the function itself. So that's what we are going to focus on. We will take this function, we will take the derivative of that function with respect to w, okay? The other way to write this is dfw, and the derivative term is dw. So we will set that, and hopefully that will help us in solving this problem, because this is the one criteria for finding minima and maxima. So let's go ahead and try to utilize this. Okay, so what we want to do is we want to set this up. We want to find this dfw by d equal to 0, because that is going to give me either minima or the maxima of the problem that we have. Okay, let me focus on that. Okay, so if we go ahead and take the derivative of this function with respect to w, there are a couple of things that you can notice, right? If you have, if the derivative of x is equal to 1, right? So that's one thing. If I take a derivative of x, that is going to be 1. If I take the derivative of 1 by x, right, this is going to be minus 1x squared. Okay, so I will take this two, information, and what I will do is I will go here. So if I go here, okay, there is 2wh listed here, and we will essentially use this 2wh information and So we will use this two entities, and then we can use this function, and we can take the derivative of this function as well, right? So if you look into this function, there is w here. So that's, if I take a derivative of w, that is going to be 1. So we will have only 2h remaining, whereas we have here 1 by w, right? And that will be coming from here. So that should be minus 1 by w square. And that's why you will see that this has turned into minus. We have 2v and this is w square, whereas v by capital H is a constant. And if I take a derivative of a constant, that is going to be 0. And that's how we derive this equation. So now this equation, or the derivative, has to be set to equal to 0, and from there we can solve for w, and that will give me a solution where the material is going to be minimal or maximum. So let's go ahead and see what is. So if I simplify this equation, you can see the t will go there 0, we will have 2h is equal to 2v by w square, and from there we will get that w square is equal to capital V by h, and from here we will basically have this solution where w is equal to plus minus h root over v by h. Now it turns out that we will not have negative dimension because w has to be positive, because the width of the tray has to be positive. It could not be of the negative dimension. So that's why we will neglect the negative sign, and the overall solution, right, which we term as an optimal solution, or w star, is going to be equal to capital V over h. Okay, square root of that is going to be giving me the overall solution. So we can use this analytical approach and we can solve for what is going to be the optimal value of w, which is defined by this equation, that will lead to the minimal amount of material that goes into making that drawer itself. Now from this information we can go and we can solve for other properties. So what we can do is we can find out, again we have w star is equal to root over v by h. We can use that information. From there we can find out all the other pertinent information that is needed to be provided to the carpenter that we have. So from here we know that L was capital V by W H, right? And we have this V by H. So here I will go ahead and substitute that root over V by H. And if I simplify this equation, that will give me the dimension, or the optimal dimension, or L star. And it turns out that L star is also equal to root over VH. So both length and width are essentially of the same dimension, and that dimension is given by the quantity root over V over H. Okay. So depending upon what values of V and H we will have this optimal solutions. And from there, we can also find out exactly the amount of material that will be needed to fabricate this optimal tray. Okay. So we can take the overall equation, which is the volume of material that is needed to fabricate the tray or the drawer, and we will substitute this optimal values for W and L, which is root over V by H here, and we can simplify this, and this is the final equation that we can arrive. And this final equation actually gives the actual amount of material that will be needed to make this drawer with all the constants, the thicknesses, the capital V and the H. So now we have derived a solution where what we have done in the overall, if we recall the hyperbola that we had, which was the solution space, right? We have found out, right, where the L and W are essentially the same. L star and the W star are, so this is L dimension, this is the, we have found this solution, and both of this are root over V by H, and that is the single solution that is going to lead to minimal amount of material that goes into fabricating the overall tray. Okay, so as you can see, we now eliminated the problem of infinitely many solutions, and we created an approach where we formulated the problem as an optimization function and set of constraints, and then we used the set of constraints to eliminate things in the optimization problem, and use the simple calculus to find the derivative and solve for this problem. And we can give this L star value and W star value, which are the single values, to the carpenter, and if he use that values, then he will be basically able to minimize the overall cost of making hundred thousands of tray and possibly save a lot of money and make profit. So this objective, where we are now coming out from infinitely many solutions and focusing on single solutions, which is good with respect to a goal or an objective, this framework is essentially known as optimization framework, and the solution approach that you saw is the focus of any optimization problem.